All right. Good morning and welcome. So this is for Science 10. Nope, Science 8. Getting you guys wrong. But this is for Science 8. We're taking a look at the states of matter. This is the PHET, the Phet.colorado.edu. This was the simulation that I had sent out on Friday for you guys to take a look at. Took a look at some of the responses and realized a little bit of confusion. So I just wanted to go over this and take a look at some of the questions and just to point out some of the things I'm wanting you to see. We're talking about matter, and matter's really, really tiny. The atoms and molecules that make up matter are really, really small. And so I thought we would, take a look at it. This is a pretty good simulation. So you got two choices, phase changes and states. I want you to go into states. And then we're taking a look at here. Now, some of the things that I want you to do is to change from K to Celsius. And so right now you can see we're at negative 259 degrees Celsius. That's pretty cold. And right now we're taking a look at argon. But let's start with water. And water's at minus 127. So we've got the buttons here. We can go solid, liquid, and gas. And it's really quick to change in between these, and we want to be able to point out some of the differences that we've got between here. All right, so I'm just reading the questions in the statement. Once the simulation has started, change the temperature readings Celsius and the atoms and molecules to water. Click on the states button. Which state has the molecules moving the most? Which is moving the least? So there we have our solid. Here we have our liquid. Here we have our gas. So in the solid, we can see that the molecules, they're just really vibrating. They're sort of twisting back and forth, but they're not spinning. They're not moving past each other. They're just there vibrating in place. I'm so excited. If we go to liquid, well, we can see now they're across the bottom, and you can see that they're spinning. And some of them are spinning quite a bit, and they're sort of moving past each other as we go through. This is at 13 degrees Celsius. And if we go to gas, well, now if you take a look at any one molecule, you can sort of trace it, and they bang into each other, they go flying off, and they're spinning, and so on. So in terms of movement, for solid, we have the least movement, and gas, we have the most movement. And all we're doing is we're changing. So this is 156 degrees Celsius. This is at 13 degrees Celsius and negative 127 degrees Celsius. So all we're doing is we're adding and subtracting energy between these things. Lots of energy, lots of space, lots of movement. Low energy, very little movement, just vibration. All right. So then number 2 says, continuing with water. Actually, I'm going to do number 3 first, because let's take a look at one of these other elements. We got neon, argon, and oxygen. Let's take a look at neon. Here we have solid, here we have liquid, and here we have gas. And so here in gas, we're still at minus 217 degrees Celsius. Neon is a gas at a very low temperature. It's a gas most of its time. And you can see they're moving past each other. With the liquid, we can see they're across the bottom, and we can see them bouncing around and moving past each other some. And they're sliding past. Oh, there's one that's even popped off. And so sometimes we'll see some of those things that they evaporate, basically. And then we have solid, and here we can see, again, they're vibrating, and we can see that the spaces, they're very closely packed together. So we can say, well, which would be the least packed? Least packed together would be here, the gas. More space between here. If we go to liquid, we can see that there's some pretty big gaps that open up between the liquid, and we go to the solid. The gaps are really, really small. This is really, really tightly together. So when we're taking a look at solid, liquid, and gas, when the particles are in the solid form, they are the most compact. The space between the molecules is the smallest, and this would be what we call the most dense. Now, if you're thinking of what I mean by density, if you think of a rock has high density. Gas has low density. Liquid has sort of a medium density. Like With a rock is going to sink. Wood has more spaces in it, and so wood floats. It's less dense than what a rock is. Rocks sink in water, wood floats in water, and you'd have to have like a helium balloon to be less dense than a gas for it to be floating upwards. Okay? So what we see here is that the most dense, the least space between the particles is in the solid phase. In the liquid, we have more space between them. You can see them moving about and banging into each other in larger gaps. Even if they're there just for a little bit, there are larger gaps between them. And then when we have in a gas, the particles are just flying around the container and filling the whole container. So sometimes we say the solid keeps its shape of itself. The liquid takes on the shape of the bottom of the container. This is like a layer of liquid across the bottom of the container, and the gas fills the container. These are the different things that we're taking a look at. The gas fills the container, the liquid fills the bottom of the container, and the solid maintains its own shape. But if we take a look at water, water is different. So if we go to gas, here we have the particles. You know, these things look like, sometimes people might say look like little Mickey Mouses. You got the two white spots and the red spot. These correspond to the elements of oxygen and hydrogen. Water, the formula for water is H2O. So the red dot that you see represents the oxygen, and the two white dots represent the hydrogens. And they know that it takes on this characteristic shape. They've been able to do studies to see that and to see that, or and they can represent it that way. So as we take a look in the gas state, we can see the molecules, they're banging off of each other, lots of space between them, and the space opens up and closes up, but then opens up again. When we're in a liquid, again, here we have it across the bottom, and we can see that there's some space between them, and the spaces open up and close up again, but they're pretty sort of tightly packed. When we go to the solid, well, notice here we have a big space, here we have a big gap, here we have a big gap, and so on. What we have are big gaps that show up within the solid. And the solid actually is less dense than what the liquid is. The solid has more spaces, more gaps there than what the liquid does. And the gas is definitely more. The gas is much, much more spread out than what the solid or liquid is, the solid or liquid. But the solid has more spaces between and is less dense than what the liquid is. And what does that mean? Well, a piece of wood is less dense than what water is, and a piece of wood floats on top of water. Since ice, as the solid form, has more spaces, it is less dense than what liquid water is, and so ice will float on water. And so in the winter, when Skaha Lake freezes over, the ice forms at the top of the lake and floats across the top of the lake, and it doesn't sink down to the bottom. Water is one of the few, to be honest, I can't even think of another material where the solid state is less dense than the liquid state. Generally speaking, the solid state is going to be more dense, and so will sink to the bottom of a liquid. Water, the solid, is less dense and floats on the top. If you take a look at oxygen, there's oxygen in the solid state, very tightly packed together. The molecules are in pairs, or the atoms are in pairs. If we go to the liquid, there it is across the bottom. We can see more larger spaces opening up. If we go to the gas, then it's filling it through. We do the same thing for argon. Argon as a gas, argon as a liquid, banging around, and then argon as a solid, just vibrating there. So water is a unique material. The solid is less dense than the liquid. The solid ice cubes float in your glass of water. So then it says, question number 4, for one of the materials, what temperature do you have to go to get the atoms to stop moving? Well, let's take neon. Okay, so here we have, and let's start it as a solid. But you can still see they're vibrating, and we're at minus 259 degrees. At the bottom here, we can pull this down, and we're adding some coldness to this. And as we make it colder and colder and colder, you can see that the vibrations slow down much greater. And here we are at negative 273 degrees, and we can see there's no longer any vibrations going. Let's take another look at a different material. Here's argon. Let's do the same thing. We pull this down. They're getting slower and slower, more and more stable. They're bouncing less and less. Still a bit of motion going on. We're getting less and less and less and less. And there we are. They're completely stopped at minus 273 degrees. Well, let's take oxygen. Let's find out what happens with oxygen. Oxygen's at minus 246. Let's pull the temperature down. They're getting less and less and less and less. And they're stopped, minus 273 degrees. Okay, let's take water. Water's at minus 127. Let's make it colder. Bring it down. Getting less, vibrating more. You can see those holes clearer. You can see how there are big gaps between the water molecules. They're moving less and less and less. Just about minus 272. We'll go to minus, yeah, there it is, minus 273 degrees. And molecules have stopped moving. Now you might say, well, come on, this is just a simulation. It doesn't prove anything. You're right. It is just a simulation. But it is based on the properties of matter. At minus 273 degrees Celsius is what we call absolute zero. And at absolute zero, we have removed all thermal energy from the particles, and the particles themselves are no longer moving. And that minus 273 degrees Celsius is an absolute lowest temperature for any matter. We can't even reach 273 degrees. We can get very, very close, but we can never actually reach it. And so here we have what matter would look like. So minus 273 degrees, like water boils at, or melts at 0 degrees Celsius, boils at 100 degrees Celsius. Oxygen, much colder than that. Argon, neon, they both melt and boil off at temperatures much less than what water does. Yet they all come to an lowest temperature of minus 273 degrees. You cannot get any colder than that. And at minus 273 degrees, the particles have all stopped moving. All right, so let's go to water, and here we are, minus 127 degrees. And it says, question number 5, if you start with solid water and add heat at the bottom, what happens to the state of water as you add heat, and what happens as you move? So here, down here, we can add some flamage, and we can see the temperature going up. And so now we've got to 5 degrees Celsius. That one, let's bring it. Okay, we get to 5 degrees, we're at 29 degrees Celsius. So now this is a liquid. You can see the particles moving and spinning past each other. We bring this down, 6 degrees, still a liquid, minus 7 degrees, and the particles are starting not to be moving past each other. Sometimes they break off still, but that's real life as well. But we have some ice forming, and they're not really working that well. All right, so as we continue adding, you can see it condenses down. 38, 40 degrees, 50 degrees, 60, 70, 80, 90, 101. So this is what we would think is boiling. And now we've got particles that are starting to float off. And we add some more particles to this. They're gaining more energy. You can see them spinning lots, and they're flying off. And so we have this gas that's happening here. And so the water molecules are taking that energy and moving them into particles that are flying off. So if we can do the same thing as removing temperature, and as the particles get colder and they move less, and as they bang in, they give up their energy, then it becomes a liquid, and we can see it condensing at the bottom. Now we'd say, well, water doesn't look like this. Well, yeah, but we're dealing with taking a look at the actual individual water molecules, we would see things like this. Here's still one more gas molecule, slowly come down. It's going to come, and it hits, and it's condensed into a water droplet. And if we drop the temperature even more, now we can see the particles. And if we remove more heat, we can see the spaces getting larger and larger, and so becoming less and less dense. All right, that's what I was wanting you to see in this simulation. And what you might want to do is to go back and take a look at the simulation, try it again, watch this video, take a look at the questions, and see how things go. All right, have a great day, and thanks for stopping in.